Welcome here, everybody. This is day 18, and it is brought to you by two letters today, actually, A and U together. They abbreviate astronomical unit, which is the distance between the Earth and the Sun. And as you can see, strictly for visual effects, at least at the beginning, we have a special guest narrator. And today's going to be a bit of a departure from what we've been doing with regards to work and energy. Today we're going to start taking a look at planetary mechanics. And of course, planetary mechanics is the study of how bodies in the solar system move and what makes them move. And the tie-in this actually has with work and energy is that eventually we're going to take a look at how potential energy, gravitational potential energy near the Earth changes as you go out to the edges of the solar system and even beyond. Now, before we start talking about planetary mechanics, let's talk about planetary kinematics. Planetary kinematics is, of course, how bodies in the solar system move and who gives a rip about what causes their motion. And planetary kinematics, they can be nicely summarized by Kepler's laws. And you've got a PDF of this. Make sure you read it. And basically, this video is just going to explain a little bit more in detail about each of Kepler's 3 laws. Okay, so let's get rid of this. Okay, bud, you can take off too. Keep looking for those chickpeas. All right, Kepler's 3 laws of planetary motion. Again, they tell you everything you need to know about how the planets move in the solar system, or how anything, not just planets, moves in the solar system. And the first law from the handout, you can see that it says bodies move about the sun in elliptical orbits with the sun at one focus of the ellipse. Okay. Now, what exactly do we mean by the focus of an ellipse? Well, if you know how to draw an ellipse, you can understand exactly what a focus is. An ellipse is basically like a circle with 2 centers. You know, if you want to draw a circle, you use a compass. The pointy end goes to the center and the pencil traces the circle along the edge. Well, an ellipse is, like I say, kind of like a circle with 2 centers. And I've got a piece of fun tack here and a piece of fun tack here, and they are going to act as the 2 centers, or the 2 foci of my ellipse. Remember, if you have one, it's called a focus. If you have 2, plural is foci. So here's the 2 foci of my ellipse, and I take a string, hang it from the 2 foci like that. Here comes my drawing instrument. And this is kind of cool. For whatever reason, I get a real boot out of this. Whoops. Bit of a problem getting around the knot there. And there we go. This produces a really nice ellipse with maybe just 2 little bumps. Big deal. But there, now you know what exactly the 2 foci of an ellipse are. And you can see an ellipse is oval shaped, it's not a circle. Okay, just for the heck of it, let's see what happens if you move the 2 foci a little further apart. So we'll try that. Okay, got to make sure my foci are firmly embedded on the whiteboard. Oh, perfect. Here we go. Watch. And you can see that if the foci move further apart, your ellipse becomes, well, more elliptical, more oval shaped. It moves further away from a circle. And of course, if the two foci are really close together, well, then your ellipse how is it going to look? You'd figure if the further apart they go, the more oval it gets. The closer together they get, the more circular it's going to get. And let's see how this looks. Oh yeah, definitely. If the two foci are close together, I won't bother drawing the whole thing, but you get the idea. If the two foci are close together, the ellipse becomes very, very close to a circle. And actually, the planet's orbits, they are they are ellipses that look kind of like this. The two foci are very close together, and the orbit is very close to being circular, even though technically it is an ellipse. Okay, so now you know what an ellipse is and what exactly the foci of an ellipse are. I'm going to get rid of this and we'll be right back and talk just a little bit more about Kepler's first law. All right, so still talking about Kepler's first law, the fact that bodies move about the sun in elliptical orbits and the sun is at one focus of the ellipse. So here we have a close-up of something's orbit around the sun, and this is not a very circular orbit, it's a very oval-shaped orbit, so it probably wouldn't be a planet, it would likely be a comet. And as you can see, when comets are orbiting the sun, when they get close to the sun, they heat up and the solar wind blows the tail off the comet in a direction completely opposite wherever the sun is. Okay? And of course, when the thing gets over here, well, it's way far away from the sun and it's not hot enough for the sun to melt the comet's material and form a tail. So out there, it doesn't have a tail. Regardless, here's this orbit. It's going around the sun. The sun is at one foci of the ellipse. The other focus of the ellipse, it is just some point in space. There is absolutely nothing there. It's not like there's going to be a little sign there that says other focus. It's just going to be some point in space. It looks like any other point. But the sun is definitely at one focus of the ellipse. And as the comet goes around, its minimum radius of orbit, or its minimum separation from the sun, that is called the perihelion. The perihelion of an orbit is a body's closest point to the sun. Of course, when it's over here and we're talking about the maximum radius of orbit, or the maximum separation from the sun, that point in the orbit is called the aphelion. And if you're talking about a solar orbit, some body like a comet or an asteroid or a planet or a minor planet, or like Pluto orbiting the sun, you're going to use the terms perihelion and aphelion. If we're talking about a non-solar orbit, like for example, say a satellite orbiting the Earth, or let's say a space probe orbiting Mars, if you're talking about a non-solar orbit, instead of using the terms perihelion and aphelion, then you use the terms perigee and apogee. Now, if you look up, let's say, the Earth's distance from the sun, what you're going to see isn't the minimum separation. You're not going to see the maximum separation. What you're going to see is the mean, or the average separation. So when you look up how far a body is from the sun, basically you're getting the average or the mean distance, which is of course going to be, you can probably figure it out on your own. It's going to be, well, this one plus this one. Added together and divided by 2. All right, I think that says everything that needs to be said with regards to Kepler's first law. We'll be back in just a second and we'll take a quick look at Kepler's second law. Okay, let's take a closer look at Kepler's second law. And again, instead of using the almost circular orbit of a planet, we're going to use the much more elliptical orbit of a comet just because it's easier to visualize. And you'll notice our comet here, when it's close to the sun, the tail, because of the solar wind, is pointing directly away from the sun. When it's far away from the sun, where it's really cold, it doesn't have any tail. And one thing about this is you can kind of see why comets take so long to come back and be visible from Earth. For example, Halley's Comet, it has an orbital period of about 75 years. I think the next time it's coming back and you're going to be able to see it is, sometime around 2050 or so, maybe 2060. But comets, if this is the sun at one focus of our ellipse, you know, the solar system, the regular planets as we know it are in here. Then comes the minor planets, the planetoids like Pluto. They're in something called the Kuiper belt. They're out here. And comets, they originate in something called the Oort cloud. And it takes a long time for them to come in, go out, and come back in again. That's a really short time, 75 years for a comet to come back. A lot of comets, they come back every 1,000 years, maybe even every 10,000 years. They are coming from way the heck out there and disappearing way the heck out there. Anyway, regardless, a little bit about Kepler's second law, which says a straight line joining the sun and a body sweeps out equal areas in equal times. So here's our comet. It's going around the sun like so. And if we follow it for some time, delta t, when it's near the sun, it goes from here to here, and you can see that its radius sweeps out some area. We're going to call that A1. When it's over here, same deal. If we follow it along for the same time interval, delta t, it moves from here to here, and its radius sweeps out some area. We're calling that A2. And Kepler's second law, Kepler noticed that A1 was equal to A2. Well, big deal. What does that really mean? Why does that help us? Well, if you think about it, if these two areas are going to be equal, okay, and these distances are way shorter than these distances, well, that of course means this distance has got to be much bigger than this distance. Okay? In other words, the comet is traveling a much greater distance in the same length of time here than it is compared to over here. Okay? It's traveling much faster when it's closer to the sun than when it is further away from the sun. So that's the important part of Kepler's second law. These two areas are equal, so that means it's got to be traveling faster over here than it is over here. So basically, Kepler's second law tells us that bodies speed up as they get near the sun. The closer they are to the sun, the faster they go. Likewise, the further they are from the sun, the slower they go. And I think that is all we need to do with regards to Kepler's second law. We'll take a look at Kepler's third law in just a bit. All right, time for Kepler's third law. Kepler's third law is the most numerical of the three, and it's probably the most useful with regards to figuring out things. And it simply says this, r cubed over t squared is equal to k. R, of course, is something's mean radius of orbit around the sun. It doesn't matter whether it's a planet, a minor planet or planetoid, a comet, a space probe that NASA put up there, one of Elon Musk thingies. As long as it is orbiting the sun, okay, we can apply this law to it. T, of course, is the orbital period. The orbital period of something is, of course, how long it takes the sun to go around once. And again, doesn't matter what you're talking about. As long as something is in a solar orbit, as long as it's orbiting the sun, r cubed over t squared is going to equal the same number, some constant. We call that Kepler's constant, and it works out to be 3.35 times 10 to the 18th meters cubed per second squared. Let's take a close look at these units. How did these units come to be? Well, of course, they follow from the calculation. If r is in meters, you're going to have meters cubed on top in your answer. Yeah, we do. If t is in seconds, you're going to have seconds squared on the bottom of your answer. And yeah, we do. For you, the important thing to keep in mind is that if you're using Kepler's third law, this equation here, if you want to use this for your k value, r has to be in meters, t has to be in seconds. If you want to use some other units, like you want to measure r in, I don't know, astronomical units, and t in, I don't know, years, okay, you can, okay, the equation still holds, but the constant is not going to be equal to that. If you want the constant to be equal to that, you got to have something in a solar orbit. R has to be in meters, t has to be in seconds. Okay, let's do a little example. Okay. And of course, the example I'm doing is right from the handout here. It says a small asteroid revolves around the sun every 30 days. So the orbital period for our asteroid is 30 days, and we're trying to figure out how far it is from the sun. In other words, what is its mean radius of orbit? Now, if you're an astronomer and you discover an asteroid and you want to be invited to all the really cool astronomy parties, you can't just point to somewhere in the sky, oh yeah, there's a new asteroid, I named it such and such. You have to be able to tell a little bit about it. Like, for example, how long it takes to go around the sun once, how far it is from the sun. So let's see if we can figure this out and get invited to all those really cool astronomy parties. Okay, well, what do we know about this situation? Well, we know that, sorry, I got to get rid of mission control here. And give ourselves a little more space. What do we know? Well, we know that r cubed over t squared is equal to k. Okay, r, that's what we want to figure out. K, we're talking about something in a solar orbit. It's orbiting around the sun. So there's what k is equal to. And what is t squared? Okay, well, we have to convert RT, our orbital period, to seconds. Remember, if we're going to use this value as our constant, our t value, our orbital period value, has to be measured in seconds. We have this one in days. So what is our t value going to be in seconds? Well, 30 days times 24 hours in a day. Okay, 30 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So there is my t value in seconds. And remember, your t value has to be squared. If I had $1 for every time someone forgot to square their t value, I wouldn't be rich, but I would probably be dining at a very nice restaurant this weekend. Regardless, I'll tell you what, I'll be right back with a little more of these calculations done, because I'm sure you don't want to watch me fumble around with my calculator right now. Okay, so continuing with this example here, we're just doing a little bit of algebra, a little bit of arithmetic. So we left off at this stage. So of course we want to solve for r. So whatsoever on the bottom here, it goes over to the other side and it goes on top. So we're left with r cubed is equal to all this. We don't care what r cubed is equal to. We know, or pardon me, we want to know what r is equal to. So you take the cube root of both sides. The cube root of r cubed is of course just r. And you're going to have the cube root of the other side. And if you do that on your calculator, make sure you can get 2.8 times 10 to the power of 10. And remember, that is r. That is the orbital radius. It is a distance in meters. In this 3.35 times 10 to the 18th, remember, there's meters wrapped up in that. So our answer is going to be in meters. And does that answer make sense? Okay. Well, take a look on your handout at this little chart here. And if you look at this little chart here, you'll notice that for Earth, the mean radius of orbit is 1.49 times 10 to the 11th meters. And this is less than the Earth's radius of orbit, which makes sense. Takes the Earth 365 days to go around the sun. Our little asteroid is going around the sun every 30 days. So that means it doesn't take as much time to go around the sun. It's got to be a lot closer. So yeah, this makes sense because it's less than the Earth's radius of orbit. And make sure you know how to get this on your calculator. I'm not going to go over exactly what buttons to push because I'm sure no one wants me to fumble around doing that kind of thing right now. So make sure you can get that number. If you can't, shoot me an email or talk to someone, and I'm pretty sure we will get it figured out. Okay, that is everything you need to know about Kepler's third laws. Naturally, there will be an assignment posted, and we will see you on Monday. Have a great weekend.